Hi everyone, I'm Janani and I'm here to talk about random order streaming lower bounds for connected components. This is joint work with Sepehr Assadi. Let me begin by introducing the streaming model. We have a graph G with vertex set P and edge set E with n vertices and m edges. The vertex set P is already known to us, but the edge set E is not given. The edges appear one by one in some arbitrary order. That is, edge E1 appears, edge E2, edge E3, and so on, all the way till edge En. This order, E1, E2, and so on till En, can be anything. We do not have space to store all of these edges because we only have space which is polylog n. This setting, where the space is restricted to order of polylog n, is called the classic streaming setting, and this is what we'll be focusing on today. There are some very strong lower bound results in this setting which we're going to talk about briefly. Even for very simple problems like connectivity and bipartiteness, it was shown by Feigenbaum, Kannan, McGregor, Suri, and Zhang that we require omega of n space. The same work also proves lower bound for some other problems which we're not going to get into, and this is not the only one. There are a lot of other results about how hard it is to process graphs in such limited space. What we're going to do next is relax the model a little bit to make it easier for the algorithms. I'm going to talk about the random order streaming model, where again we have graph G with the vertex set known to us, but instead the edges appear in a random order from E. We have edge EI1, edge EI2, and so on till edge EIN, where this order I1, I2, and so on till IN is chosen uniformly at random. So in this random order stream, the problem we're interested in is to find the number of connected components in the graph up to an epsilon n additive factor approximation. Even in this random order setting, solving connectivity requires omega of n space, and this was shown by Chakrabarty, Cormode, and McGregor in 2008. I'm going to talk about some prior work for this problem in this setting. It was shown by Peng and Solar that you can solve this with 1 by epsilon raised to order of 1 by epsilon cube times log n space in 2018. And this was later improved to 1 by epsilon raised to order of 1 by epsilon times log n space by Chiplanker, Kaprov, Kalher, and Price in 2022. The CKKB 2022 paper also gives strong evidence for a lower bound on the space required. They define something called a batched random order stream, where instead of the edges appearing in a purely random fashion, they're first grouped adversarially into groups of size 2. These groups then appear in a random order. This is harder for the algorithms because this grouping can be adversarial, but it is an easier model to prove lower bounds against than the random order streaming model. So in this model, the CKKB 2022 paper showed that to find a connected component, you require 1 by epsilon raised to omega of 1 by epsilon space. So this lower bound does not apply to estimation of number of connected components, and it does not apply to random order streams. I am now going to talk about our results. We showed that there is no algorithm which estimates the number of connected components up to epsilon n additive factor in 2 raised to little of 1 over epsilon space for every epsilon greater than 0. This shows that this exponential dependence on epsilon, which is present in all the previous algorithms, is actually necessary for this problem. The main underlying graph we use and the problem is called gap cycle counting, which I'm going to define now. We have two different cases. The graph can either have n over 2k cycles of length 2k each, or it can have n over k cycles of length k each. That is, the graph is entirely made up of cycles of length 2k or cycles of length k, and we want to distinguish between these two cases. We're going to add some noise to these instances. That is, the graph is still going to contain cycles of length 2k, But in addition, it is also going to have paths of length k. And the same is true for the other case as well. So now, half of the graph vertices are going to be split off and counted as noise, and they will form paths of length k, and the other half are still going to form cycles. More concretely, the graph now contains either n over 4k cycles of length 2k or n over 2k cycles of length k, and in addition, it's also going to have n over 2k paths of length k. So what is the relation between this graph and connectivity? In the first case, the total number of connected components is n over 2k for the paths and n over 4k for the cycles. And in the other case, it's n over 2k again for the paths and n over k for the cycles. There is a difference of n over 4k in the number of connected components. So if epsilon was less than 1 over 8k, we can actually distinguish between these two cases with just the estimation of the number of connected components. I'm going to talk a little bit about this problem. This was introduced by Verbin and Yu in 2011 to prove single pass streaming lower bounds. And it was later used by Huang and Peng in 2016, Kapralau, Khanna and Sudhan in 2015, and a lot of other results for the same purpose. It was extended to multi-pass streaming lower bounds by Assadi, Cole, Saxena and Yu in 2020, and also by Assadi N in 2021. All of these prior results only look at NGC from an adversarial point of view. They do not study it under random order streams, and we are going to do that today. We have graph G, which is an instance of NGC, and we have Alice and Bob. What we're going to do is randomly partition the edges of G and give them to Alice and Bob. Alice gets edge set EA, Bob gets edge set EB, where EA and EB are just a random partition of the edge set of G. Alice can send a message of length at most s to Bob, and Bob has to find which instance of NGC the graph G belongs to. So let's see how you can use an algorithm in random order streams for connectivity to solve this problem. Here, if you have an algorithm which uses space at most s, what Alice can do is pick a random permutation of EA, run this algorithm A on this edge set, and send the memory state of A to Bob. What Bob can do is again pick a random permutation of EB, run this algorithm on this order of EB, and output the answer from A. This way, we can actually emulate a random stream of the edges if we partition the edges randomly between Alice and Bob. So after this, we're only going to focus on proving a lower bound for NGC of omega of n, because we pick k, which is the length of the cycles, to be theta of log n, and the approximation factor epsilon to be theta of 1 over log n. So proving a lower bound of omega of n is actually equivalent to proving a lower bound of 2 raised to omega of 1 over epsilon. Now I'm going to talk about our techniques. The two main things we're focusing on today is the gadget construction for hard instances of NGC, and then reduction of these hard instances to an XOR of index problem. So for the gadget construction, we're going to need to encode one bit using a group of 4 vertices. We have vertex group left, which has 2 vertices, and right, which has 2 vertices again. And if this bit is 0, we're going to connect U1, the first vertex of the left group, directly to V1, the first vertex of the right group, and again U2 directly to V2. If this bit was 1, we're going to cross out these edge connections, and U1 is going to be connected to V2, and U2 is going to be connected to V1 instead. So this way, we're going to use 4 vertices to encode this one specific bit. The next step is to extend this encoding to any string. So if the string is of length n over k, we're going to use 4n over k vertices to encode this string. For example, if this string was 0, 1, 0, we're going to have 3 different sets of 4 vertices each, where each set encodes 1 bit. The first group, U1 and V1, encodes bit 0, u2 and v2 encodes bit 1, and u3 and v3 encodes bit 0 again. And this can be done for any length string. The next step is to permute a string, and we'll see what I mean by that shortly. We're going to be given a string x and a permutation row from Sn over k. The graph on the left is the gadget we constructed for the string already, and we're going to embed this in a gadget for row. I'm not going to talk about what this specific gadget for row is because of time constraints. I'm only going to talk about what the final effect of it will be. So we'll have two different gadgets for row, and this gadget for x is going to sit between them. This construct is going to be called a block for us, on input x and permutation row. Let's look at some properties of this block. We have this string x, and this block is also going to have groups on the left and right, u1, u2 and so on till un over k on the left, v1, v2 and so on till vn over k on the right. The paths between these left and right groups is again going to encode another string for us. So what is this string? We're going to use row to permute x. What do I mean by that? We're going to have a new string y where in its first position we're going to have the bit which appears in position row of 1 of x. In its second position we're going to have the bit which appears in position row of 2. And this is going to go on all the way to the last position, row of n over k. So this new string y is also a string of length n over k and is just x permuted according to row. What we want out of this block and this gadget for the permutations is that the connections between u1 and v1 encodes bit y1, u2 and v2 encodes bit y2 and so on till un over k. More specifically, if this bit y1, which is the same as x row of 1, was 0, the first vertex of u1 is going to be connected to the first vertex of v1, and the second vertex of u1 is going to be connected to the second vertex of v1. If this bit was 1 instead, the first vertex of u1 is going to be connected to the second vertex of v1, and the second vertex of u1 is going to be connected to the first vertex of v1. That is, the connections between the group u1 and v1 is going to be crossed. The same way, each such pair ui and vi is going to encode bit yi of this new string. And we're going to construct gadgets for row so that this can happen. What we're going to do next is put multiple such blocks together based on different strings and permutations. We're given theta of k strings, x1, x2 and so on till x theta of k, all of length n over k, and we're again given theta of k permutations. We're going to construct blocks which each such string and permutation x1 row 1, x2 row 2 and so on till the last pair. And here we're only going to focus on the leftmost group of this first leftmost block and the last group of this last block and see the connections between them. The effect is going to be that the connections between u1 v1, u2 v2 and so on till un over k and vn over k is going to store another string z for us, which is just the XOR of all these different y's which the blocks themselves store. In more detail, if the first bit of z is 0, which is just coming from the first bit of y1 XORed with first bit of y2 XORed with the first bit of y theta of k, the first vertex of u1 is going to be connected directly to v1, and the second vertex of u1 is going to be connected directly to the second vertex of v1. The paths between vertices of u1 and vertices of v1 are just going to connect the corresponding vertices in these groups to each other. If this bit was 1 instead, the first vertex of u1 is going to be connected to the second vertex of v1, and the second vertex of u1 is going to be connected to the first vertex of v1. The path connections between these groups is going to be switched. So this way, every pair again, u2, v2, u3, v3 and so on, encodes one specific bit of this string z. Now that we have this, let's see how we're going to get the actual MVC instance out of it. First, let's see how you can create cycles. Let's look at one specific group, U1 and P1, where the gray area denotes the part which comes from the blocks. This encodes bit Z1, and if this bit was 0, we're going to have direct path connections between these corresponding vertices. What we're going to do is add edges between the first vertex of U1 and the first vertex of V1 and the second vertex of U1 and the second vertex of V1. Once you add these edges, the net effect is going to be that if this bit was 0, we're going to be creating two different cycles of length k, and if this bit was 1, since the path connections are crossed out, we're going to be creating one cycle of length 2k. If we do this for half the groups and leave the rest of the groups as it is, the rest of the groups in the latter half is going to form paths of length k minus 1, which is the noise we wanted. And the first half is going to create cycles based on the bit they're encoding. So in more detail, if you look at just the first half and pick random strings and permutations, it's going to give you a jumble of 2k length cycles and k length cycles because these bits can be 0 or 1. Since we want cycles to have the same length, what we're going to do is ensure that all the bits in the first half are completely 1 if we want cycles of length 2k, or all the bits in the first half are all 0 if we want cycles of length k. And this is how we get the final instance. Just to recap, we have these blocks made of permutations and strings which actually have the net effect of encoding a permuted string x permuted with rho, and then we concatenated multiple such blocks together to get the final instance, and we added edge connections between the left groups and the right groups with their corresponding vertices to get cycles. After this, I'm going to look at analyzing this instance and reduction to XOR of index very briefly. So as we said earlier, all the bits in the first half, Z1, Z2, and so on till Zn over 2k are going to be the same, right? What an algorithm should do to solve this NGC instance is find one such bit, because it will tell it whether these cycles are of length k or length 2 or 2k. What it can do is, if it can find just one such bit specifically with very low advantage, say k over 2n, then with a union bound, it's actually going to find at least one bit and solve the problem. So there is a way to formally translate this with a hybrid argument, which says that if you want a lower bound for finding one bit among any of these n over 2k bits with constant probability, it is just as hard as finding one specific bit with this very low advantage k over 2n. We're not going to go into details about this. What we're going to do now is just prove a lower bound for tracking one bit, which is just the bit z1, with this very low advantage of k over 2n. Now let's look at what is going to happen to this graph under a random partition of edges between Alice and Bob. So any such path in this graph is going to look like this. Some edges belong to Alice, some edges belong to Bob, and we cannot control which order or which edges are given to Alice and Bob. Let's look at what's going to happen to these blocks under a random partition of the edges. Some information about x goes to Alice and some information about x goes to Bob, and this is true for the permutations as well. What we want to happen is that most of the information about x should go to Alice and most of the information about rho should go to Bob. This is what we call a desired partition or a good block for us, and we can prove that a lot of these blocks actually are good and are favorable for us. So once we have these good blocks, if there are bad blocks, we're just going to ignore them and fix the output on these bad blocks and just look at these hard instances, which are the good blocks. The effect of this is going to be that Alice is going to have some strings of length theta of n over k, and Bob is going to have some permutations from s theta of n over k, they want to find the first bit of this string z, which we defined earlier. So what we want is to prove a lower bound of omega of n for this problem against an advantage of k over n. And this is possible using tools from Fourier analysis over the hypercube and the KKL inequality, which was proved by Kahn, Kalai and Lignan in 1988, and then later used by de Wolf for this problem. So using this omega of n lower bound, we can actually translate it all the way back to an omega of n lower bound for NGC, which is what we wanted. I'm going to conclude this talk now. What we showed was lower bound of 2 raised to omega of 1 over epsilon for estimation of the number of connected components up to some epsilon and additive factor in random order streams, showing that this exponential dependence on epsilon cannot be avoided. There are still some open questions left here. Can we prove a factorial lower bound of 1 by epsilon raised to omega of 1 by epsilon? And can we prove a lower bound for NGC when the cycle length is theta of log n over log n? Thank you for listening.